Good day. So, today we will talk about IP version 4, that is the Internet Protocol version 4. This Internet Protocol is really the network protocol of the entire stack, and actually is at the heart of data communication. And as it turned out that it became so successful that also other kinds of communication like voice, video, etc., they are also coming over to IP in a big way in many segments. So, today we will talk about the IP version 4, and just a quick review of the stack. That IP, or the so called Internet Protocol, is designed to connect networks that are possibly managed by multiple organizations or people. Okay. The internet that we see today, that is a connection of networks. So, it is a various networks. So, various networks naturally are owned by various different organizations or people, and they are so managed by different people, but they, if they have to communicate, they somehow have to come together and agree to one central protocol, one central network layer protocol, and IP is that protocol. It may have different physical connections. Naturally, if there are different networks having different connections, so it may have different physical connections, and it may be connected via a sequence of arbitrary intermediaries. Arbitrary intermediaries in the sense that when you are communicating from one, say, computer to another computer, these two networks also may not be directly connected, they may go through other intermediate networks. So, there may be a number of hops before your communication reaches its destination. As we have discussed earlier, because this we have discussed in the very beginning about that layered approach, which is used to simplify the application. We just quickly have a look at the layered approach. This is just an example. Let us say we have HTTP, which is the protocol used in the application layer for web. So, this HTTP protocol, this may use a TCP connection, alright. So, TCP, this is another layer, this is called the transport layer. So, we will talk about this later, which communicates with the IP and which then may communicate with Ethernet. But you please note that below the IP there may be a multiplicity of different data link layer protocols, like Ethernet is one, tokening is another. So, they can communicate because of this integrating protocol IP, which is common to both. So, it is a single protocol at network level, ensures packets will get from source to destination while allowing for flexibility. So, we have this so called hourglass design. So, we have this FTP, HTTP, TFTP, etc., all these different application layer protocols at the top. Then we have the transport layer. So, there are two common protocols are TCP and UDP over here, but all of them to integrate to one single network layer protocol, namely IP, and this IP may connect to naturally different networks running different data link layer protocols. Just to look at how the encapsulation goes, once again we had discussed this earlier, maybe in the first or second lecture. So, suppose we have the user data which is being fed to maybe some application. So, there is now that particular application will have its own header. This header information is what is used for a protocol between peers at the same layer. So, the application layer of this host will communicate with the application layer of the other host through this application header information. Then this is passed to the transport layer, where the TCP, if the TCP is the transport layer protocol which is being used, then TCP header gets added, and then it is passed to the network layer. So, this is while coming down, while something is being sent. So, this is the IP header gets added at the network layer. So, so far as the IP protocol is concerned, this entire thing containing the TCP header, application header, user data, etc., is the payload. Similarly, for TCP, the application header, user data together is the payload. So, whatever is inside the TCP is not really concerned with that. Similarly, IP considers this entire thing as the payload, and then it sends to the next layer, which may be Ethernet as an example. Ethernet adds a header as well as a trailer. We can see some of the overhead that we incur in this. For example, this TCP header is 20 bytes, IP header is 20 bytes, Ethernet header is 14 bytes and it has got a 4 byte trailer. Okay. And then this entire thing is payload for the Ethernet, which has a minimum this thing of 46 bytes to 1500 bytes, etc. So, this is how it comes when it data is being sent. When data is being received, it is in the other way. The first layer will take out the first these two headers and trailers, then the IP layer will take out the IP header, look at it and pass it up, TCP header, that will get stripped, and finally the user data finally it will reach the application layer. So, looking at it the other way, that means suppose we have the Ethernet driver, this is really the lowest level. So, here the tree has been shown upwards. So, in the when something comes to Ethernet, well, it has so many network protocols in the next layer, but these ARP is the address resolution protocol, which is that given an IP address, what is the MAC address. This is the reverse of that, that given a MAC address, what is the IP address. Anyway, so these are used for communication within the same network, but otherwise most of the traffic comes to IP. And then above the IP layer, this TCP, UDP, IGMP, this is for multicasting, we will talk a little bit about this later on. ICMP, Internet Control Protocol, we will talk about this little bit later on. So, this and mostly the applications really, these are for control and multicasting functions, but the major part of the communication comes through this TCP and UDP, and they connect to the various applications which may be running at the application layer. So, this is how it is demultiplexed. Just to summarize this IPv4 protocol, we have IP is a best effort connectionless protocol, it is a best effort. Okay. That means that the intermediate nodes will try to get your packet to the proper destination as best as possible, but if it is not possible, it will drop the packet. Okay. So, this does not give you any guarantee about the delivery of the packet at the other end, but it is understood that all the nodes in between will make its best effort. What does that mean? Okay, it may mean that suppose you consider a router which is somewhere in the network. Now, it is receiving packets from so many sources and they are destined to so many other different networks. Now, it may so happen that because of the pattern of communication, the router may get congested. So, if it is congested, so many packets are coming in, it just cannot hold them in its buffer any longer. So, it will be forced to drop some packets, alright. So, although it will make best effort, but then it is not this is not a guarantee. And then secondly, this is connectionless. You remember about connection oriented and connectionless protocols. For example, our telephone network was a connection oriented protocol, but here this is a connectionless. That means from the source to the destination there is no guaranteed physical or virtual connection between the two, alright. So, what would happen is that if you are sending a stream of packet from one source to the other, what might happen is that some of the packets may take one route and then some of the other packets may take another route. They may reach all of them may reach the destination, but they may get out of order and so on. But so this is all a part of the connectionless protocol. It is a datagram or packet oriented protocol. You can get an IP packet from anyone without any setup or connection establishment. Packets are normally routed using destination routing. That means the destination is known and how to get to the destination, that is what is stored in the routing tables. You specify where the packet is to go, now not how it gets there. Now, there are some more parts. You can optionally specify source routing. That means at the source itself there is a provision in Internet protocol, that in the source itself you specify that this is the route through which it will it should reach the destination. It is possible to do that. For example, if you remember, our BGP uses source routing, but anyway in general for internet packets it is possible to do the source routing, but this is somewhat limited because the number of hops you can specify becomes restricted because of some limitations of IPv4 IP version 4 protocol structure. We will come to that later on. And each packet is routed independently. That means they can be delivered out of order or might not be delivered at all. Now we come to this important topic of IP addresses. Okay. The IP address is a 32-bit address, that is 4 bytes. Okay. 32-bit means 4 bytes. It identifies the network and the host on a given network. Divided into 2 parts. First part identifies the network, the second part identifies the host in the network. The form is not the same for, if the format is not the same for each address. Okay. So, this is an important point to understand, that when you are given an IP address, it is a 32-bit address. This 32 bits is actually divided into 4 bytes, okay, and each byte is usually read out or in decimal separately. Okay. So, you can get a IP address like 144.16.19.23. Okay. So, this 144 is the decimal equivalent of the binary string which is in the first byte of the address. Then 144.16 dot is just separates the 2 bytes. So, 16 is the next byte. So, next byte contains the decimal binary equivalent of 16. So, if you convert this 144, 16, 92 and 3 separately into binaries into bytes, that means binary strings, and put them together, that gives you the 32-bit address. So, or in other words, the 32-bit address is usually read out this way. Now, in this in these 4 bytes, okay, there is some part in the more significant part of it, then some part which specifies which network you are in, and there is some part which specifies that which is the host in that particular network. Okay. This is the same concept as if you think about in a postal system. Okay. So, in the postal system you give the name of the town and then you give the name of the street or the house, all right. So, the people outside will not really know about the streets in a distant town, okay. They will just look at the town name or the so called pin code and just simply send it there. Then those people will figure out where is it that this house or this street is in that particular town, okay. So, we have a network part which is usually mostly seen by people, which is important for people who are outside, who are trying to route into this network, and then there is a host part which is important within the network. So, once it has the packet has reached this particular network, then it has to reach a particular host. So, that is where the host part comes in. Okay. There are 3 types of addresses in one sense. Okay, there are other classifications, we will come to that later on, but one is that it is for unicast communication. Unicast means it is destined for a single host. So, it is originating somewhere and it is destined for a particular host. Otherwise, there is broadcast communication, it is destined for all hosts on a network. So, in a particular network, if you want to send some message to everybody, then you can use this broadcast communication. Or there may be multicast communication, this is destined for a set of hosts. Okay. This is a subset of all hosts which are there in that particular network that belong to a particular multicast group. So, that is called multicast communication. As I have already explained, the 32-bit number is represented in the following format. That means there are some something dot something dot something dot something, where XXX is the decimal representation of the binary bit string. For example, say 144.16.7.4. So, 144, if you see the first byte, so there is a byte. So, this is one, this has got a place value of 128 plus 16 for these two ones. So, that makes it 144. This is, so this is the binary equivalent of 144, or 144 is the decimal equivalent of this. So, this is the IP address, 4 bytes of it, and the corresponding decimal equivalent of each of the bytes is given 144.16.7.4. So, this looks like a valid IP address. As for another classification of IP addresses, okay, so they are divided into 5 classes. These 5 classes we are, by the way, we are talking about IP version 4. Okay, so in IP version 4 there are these 5 classes A, B, C, D, E, where A all class A addresses start with 0. So, it has a prefix of 0. Class B has a prefix of 10, class C has a prefix of 110, class D has a prefix of 1110, and class E has a prefix of 4 ones. So, you can see that they all have unique prefixes, and by looking at it you can make out what it is. Irrespective of what values are here, you can make out which class it is. Now, as I said that an IP address contains two parts. The first part is the network ID, and the rest of it is the host ID. Now, just consider the class A address. Class A address, so the first byte is given to the network ID, and of course, of the first byte, the first bit is 0, indicating that this is a class A address, and then so you have 7 bits left for a network ID. So, you can have at most 127 or 126 networks as a class A, because that is because you only have 7 bits to represent it. And in each of these network, the host ID has a has 24 bits for specifying the address of the host in that network. So, for 24 you have actually 2 to the power 24, which is about 16 million. So, a particular class A address, I mean if you have if your organization has a class A address, which is very unlikely, but anyway if your organization does have a class A address, then this is one of the 127 networks that could be there worldwide, big networks, real big. How big? Well, as many hosts as are there in the network, and how many hosts can be there. For the host address part, we have kept 24 bits, which means that there can be a possibility of 2 to the power 24 or about 16 million hosts. So, there could be a network with 16 million computers in it. Okay. This is very I mean unlikely, nobody has such a big network. Anyway, we will come to that part later on, but this is how a class A address is specified. So, next we go to class B, which is in the same way, but here instead of 1 byte for specifying the network, we have 2 bytes for specifying the network. Out of these 2 bytes, the first 2 bits is 10, so that is already gone, and the rest 14 bits are for the network ID. So, 2 to the power 14 is about 16,000. So, you can have 16,000 different class B networks, and in each network can contain 2 to the power 16 hosts, which is about 64,000 hosts. So, these are also big networks, fairly big networks, but I mean there are networks which are of that order, but you have only 2 to the power 14 or 16,000 such networks, you cannot have more. For class C, 3 bytes are given for the network part and only 1 byte. So, a class C network can have only 2 to the power 8, that is 256 hosts. So, that is a real small network, okay. But you can have a large number of them, namely you can have about 2 million such networks, 2 to the power 21. Class D is for multicast group, and class E is really experimental. So, they start with 1110. So, after 1110, the entire 28 bits is for specifying which group, but this does not work very well. So, we will come to that later on. So, if you see since you see that if you the class A range as dotted quad, so A is 0.0.0, of course, all zeros is not a valid particular address, but anyway. So, we are giving the outer limits of it to 127.255 etc. So, so by looking at the first decimal number which is corresponds to the first byte, we can immediately make out that whether this is a class A, class B, class C or class D etc. address, because a class A address cannot be more than 127, and if the first digit or the first decimal number is less than 127, less than or equal to 127, you know that, or less than 127 actually, then you know that this must be a class A address. If it is from 128 to 191, then you know that this is a class B address, and so on. So, by looking at the first decimal number, which is the equivalent for the first, because you see the first byte is being dictated this way depending on the class of the address. So, that is how they come to a particular range of numbers. So, looking at the first number we can know that which class of address it is. Okay. So, this class A, now that is obvious, used for small number of networks and large number of hosts, very small number of networks actually. First byte represent the network address, this we have this thing, last 3 bytes represent the host address. Class A address have a first bit of 0 and class A network addresses range from 0 to 126. 127 is actually reserved for something else. Class B, it provides an equal number of networks and hosts. First 2 bytes are network address and last 2 bytes are host addresses. First 2 bits of a class B addresses are 1 and 0. So, you can only have 16,000 such class B networks, and network address range from 128 to 191, that is the first decimal number for the first byte. Class C is a greater number of network addresses, fewer host addresses. First 3 bits are 110. So, network addresses range from 192 to 223. Class D is used for special multicast addresses, first 4 bits is 1110. We will talk about multicasting later on in some more detail. Class E is used for experimental purposes, first 4 bits is 1111. Okay. Now, there are some special addresses. So, special source addresses as part of an initialization procedure, for example, boot P. This host on this network, this is net part is 0 and host ID part is 0. That means, well, when I say the net part is 0, now depending on which class of address it is, the entire network, suppose it is a class C address. So, the first 3 bytes are really the network part. So, it will be 0.0.0 and the host part is 0. So, if you say 0.0.0.0, it means that if you say that it means yourself, that means whoever is saying 0.0.0.0, he is meaning himself, alright. So, this is sometimes required. For example, in boot P protocol you require to refer to yourself. Specified host on this particular network. So, you keep the network part 0 and the host ID for this particular host that you want to specify. Suppose this is a class C address. So, in a class C address the host part is given only by the last byte. Suppose the last byte has a decimal value of whatever, let us say 130 or something. Okay. So, if you say 0.0.0.130, that means whatever the network I may be in this particular network, get me the host numbered 130. So, that is the meaning. So, this host, so it is a specified host on this particular network wherever it is. Loopback address. Loopback address allows applications on same host to communicate using TCP/IP. Now, here the net ID is given as 127 and host ID could be anything, which means that if the net ID is 127, that means the first byte is all ones. Okay. That is a loopback. That means this is referring to this particular host. Why do you require this? Suppose 2 different applications are running on the same host, and these 2 applications, they want to communicate with each other using TCP/IP. Now, why do they require TCP/IP? If they are sitting on the same host, they could communicate directly. Well, yes, but the point is that these 2 applications could have been hosted in 2 different hosts also. If that were so, then they would have to use TCP/IP. So, instead of writing 2 different versions, one for the case where both of them are in the same host and the other for the when they are in 2 different hosts, you write the same program, use the same TCP/IP stack. Only thing is that you want to refer to the same host as you are this thing. So, if you are trying to refer to the same host using the same TCP/IP, but how do you know where to which is the network address, etc., etc. I mean, you would not in general like to make changes to the hardware a particular number into the application. So, there is a way to refer to the same host, which is by using 127, that is all ones in the first byte. Then we were talking about, you remember that we said that there are the, 3 different types of addresses for unicast, broadcast and multicast. We have seen about unicast communication, that is the network part and the host part, both you indicate, and then you are really talking to that particular host. We have seen about multicast in class D and class E addresses, class D mostly, class D addresses. So, that is a multicast group. And then now you talk about broadcast, but here there is a caveat in the sense that you cannot broadcast, you are not allowed to broadcast to the whole wide world. Why is that so? Well, because if everybody or even a very limited fraction of people start broadcasting some message to everybody in the world, then the entire network will be swarmed with broadcast, because now in this age of internet millions and maybe billions of people are getting connected to the internet. So, if only a small fraction of them want to broadcast things to everybody, that is not, that cannot be allowed, because then the entire network will go down. So, there is you cannot broadcast to everybody in the world. So, broadcasts are always limited, and how they are limited and how the broadcast addresses are specified, this is what I will discuss now. Limited broadcast typically used for initialization, only appears on local cable or collision domain. Net ID is -1, that is all ones, and host ID is all ones. Okay. So, which means that if you put if you give an address which is all ones, okay, which means that you want something to be broadcast in the local network wherever you are in. A net directed broadcast, you want to broadcast to a particular network. So, this is forwarded via router. Net ID, so now that particular network has to be mentioned. So, the net ID, the network address part has to be specified giving the net ID. Host ID is all ones. So, you can see that all ones mean that to everybody. So, that is the broadcast this thing. So, all ones means to everybody, but if you put all ones in network part as well as all ones in the host part, it cannot mean that all networks and all hosts in all networks, that is not allowed, as I said. So, all ones in the network part as well as all ones in the host part mean that to all the hosts in this particular network. And then there could be a subnet directed broadcast. We have not talked about subnets as yet, which we will do. So, this will give the so the net ID will be particular net ID. There will be a subnet ID which is really carved out of the host part of the address. We will come to this, that gives the subnet ID, and then host ID part will be all ones. So, this is just by another look at it. So, all zeros means this host, all zeros in the network part and the host part is something specific, a particular host on this particular network. All ones means broadcast on the local networks. If the networks part is specified and so host part is all ones, that means broadcast on a distant network. If it is 127, that means all ones on the first byte, and anything in the rest of it, that is a loopback. Now, we come to a problem. Okay. First is specifically a few companies got class A, okay, like Xerox and some other companies, they got a class A address when they were actually very closely involved with designing internet in the beginning of this thing, when in the ARPANET days. So, they were there from the beginning. So, at that time people really did not know, the people who designed this network, they had no idea that their project is finally going to blossom so wildly and become so greatly successful. So, they had no idea that they had to be careful with all these addresses that they were doling out. So, the companies which came in, they had got some class A addresses. You remember, the class A address can have 16 million hosts, which is really much bigger than anything a particular company might want. That is only one part of this. Many institutions got class B networks. How many? Well, as I said that for 14 bits, so you can have only 16,000. So, 16,000 is not such a big number when you are talking about in the global scale. So, 16,000 institutions and maybe 126 companies over there, that is really a small number. But nowadays everybody, okay, there are millions of companies now, or and many thousands, at least hundreds of thousands of companies who want to have their own network, etc. Now, they are now reduced to accepting only class C address. Now, class A address is too big, because you cannot have 16 million hosts, but a class C address can accommodate only 256 hosts, but 256 is a very small number. Okay. Any institution or many institutions nowadays have got many thousands of computers in their network. So, this is too small for them. Okay, first we will, how to handle this part, we will come to that later on, but for the first one, just think of another problem. Suppose you have a class A or even a class B network. Suppose even in a class B network where you have 64, you can have 64,000 nodes. Suppose if you don't, even if you do not have 64,000 nodes, suppose say you have 10,000 nodes. Now, if all these 10,000 nodes is one network, remember that what is a network in our parlance at this particular moment? Well, that is one particular broadcast domain. You can always broadcast in this network. If you want to communicate to some other host, if you are sitting in one particular network, you communicate to some other node in that particular network, you need to know his MAC address, which you do not, but you know his IP address. So, what you will do is that you will broadcast the MAC address, that is the ARP protocol, asking for the broadcast the IP address, asking for the MAC address. Now, whichever machine has got that particular IP address, he will catch it and answer with his own MAC address. Okay, that is how the ARP protocol works. Now, if 10,000, so whenever you try to communicate, if you do not know the MAC address of the other side, naturally you will send a broadcast to the entire network. Now, if all these 10,000 hosts start sending broadcast messages from time to time, then even that is too much for the network. Okay, the broadcast traffic would be too much. Okay. So, what we have to do is that since the network is so big, we have to break it up into smaller parts, so that broadcasts are limited to smaller, what we call sub networks. So, we have to break up this network into sub networks, so that broadcast can be contained. Now, in order to do that, you need some more bits to. So, now in the same principle, previously we were talking about the two parts of the address, one is saying this network, and then we are saying this host in this network. Now, we have to say three things: this network, this particular subnetwork in that network, and then this particular host in that subnetwork. Just like instead of a town, let us say if you have a city, in a city there will be a large number of post offices in the same city. Okay. So, if from outside, maybe from another country, they will send it to that particular city. In the city, you will decide, okay, this is that particular post office in that city, and that particular post office would know, okay, this particular house on this street in this region. Okay. So, that is how it is. So, we have a network, we have a subnetwork, which is a part of which is a breaking up of a big network into smaller subnetworks, and then we have a host in that particular subnetwork. Okay. So, as we have said that for broadcast would go to an entire network, obviously impractical for a class A networks, even for class B networks it is impractical. So, subnets are used to divide a large network into smaller networks. Each address allows for one network address and many hosts, that is all hosts are on the same network. Subnet masks are used to create many subnets within the same network address. So, we will look at subnet mask. So, this is a bit string applied to an address. If the bit is 1, the corresponding bit in the address is considered to be a network bit. The network mask is known only locally. All right. So, what we do is basically this. Suppose we have one part which is the network part, next part which is the host part. What we do is that we take some bits from the host part. So, we take some bits from the host part and use them for specifying the subnetwork. So, and this subnetwork, so how many bits of the network which you take for the subnetwork, that is given by the subnet mask by placing those particular bits to be 1, and this subnet mask is known only locally. So, this is an example. suppose we have a class B network. In a class B network, you know that the first 2 bytes is the network part, the other 2 bytes is the host part. Now, in this host part, let us say we take it that the first 1, 2, 3, 4, 5, 6 say these 6 bits will show my subnetwork address. So, you make the corresponding bits in the network mask to be 1, okay, and the rest are all zeros. The host part, all the host parts are zeros. Okay. Now, looking at the address, we will know that since we will know that this is whether it is a class A, B, C just by looking at the first number. So, we know how much is the network part. If we know the subnet mask, we know how much is the network and subnetwork part. So, if we take out the network part from that, we get the subnet address here. So, so these are the actually this is not the address, the masks only tells you that these are the bits which are used for the subnet address and the rest of it is for the host address. We will see examples of this. Let us say we have an IP address 144.97.16.132, that is the IP address of a particular host, and we are also told that we have a subnet mask of 255.255.255.192. Well, 255.255 etc., this is all for only human communication. Of course, these are individual bytes which are to be converted to the corresponding bit strings. The 255 are all ones in the byte. So, all ones, and 192 is 128 plus 64, that is the first 2 bits are 1, the rest are 0. So, we know that we have this is the subnet mask. Since this is a class B address, we know that this part of it, if you convert that 144.97.16.132, this is the string you get. So, 144 is 120 etc. So, so the first 2 bytes is for the network part. Now, we also know that the 8 plus 2 10 bits are for the subnetwork part. So, this is a subnetwork address that I am talking about. So, 0001, 0000 and 10, this is the subnetwork, and which host? Host is this 100 part. So, the network part is the first part, first 2, and then the subnetwork part 000, 100. So, this is the entire network part wherever we have a 1. Beyond the point where we have a 1, we put all zeros for the network address. So, the network address is 144.97.16.128. This is 144.97 is telling me which particular network. 16.128 is telling me which particular subnetwork within that network, and the host is finally this simply this 100. So, the host is 4. Let us just see another example. So, we have this IP address which is 144.97.17.132, subnet mask is this. Suppose this is this is the subnet mask. So, we see that the first 7 bits. So, the network has been broken down into 127 different networks, and then we have the hosts, 9 bits for hosts. So, we can have maybe 512 hosts in each network. So, this is the network part up to this one. So, we take all the ones which are there, rest we put it as 0. So, network is 144.97.16 and host is 1.132, okay, that is the host. So, how does packets get to the other end? Select router based on the IP address, that is for class B use the upper 16 bits as a network specification, for class C use the upper 24 bits as network specification, and so on. Naturally, for class A just look at the first 8 bits. Route to that network using the routing tables as we have seen. So, depending on whether it is a class A, class B or class C, you use 1 bit, 1 byte, 2 byte or 3 bytes as the network address, route to that network using routing tables. So, using this routing table, and if your routers are working all right, if your RIP or OSPF or whatever is working all right, then it will reach that particular network. The point is what happens after that? Then that router uses the pre-specified subnet mask to select a subnet, because looking at the subnet mask and looking at the IP address, it knows that how many bits are there for specifying the subnet. So, it finds the subnet mask. So, it just takes out the subnet part of the address, which is looked up in a subnet routing table. A subnet routing table is consulted and traffic is directed to that particular subnet. So, this gives you a more hierarchical structure, and ARP broadcasts are contained within the subnet. So, that is this thing, and of course, if you reach that particular subnet, then the host number is given, then you go to that particular host. Now, now we come to the other part of the problem. As I mentioned that this class A is of course huge, class B is also very large. So, we have to break them up into these sub networks and all that. The other side of the problem is that these class C networks, the class C address is very small, alright. Class C address is very small, that is one thing. And the other thing is that the network has grown so much, there is a tremendous demand for IP addresses. One thing you must remember, that these IP addresses have to be a global standard, okay. You cannot have your local standard, because other people will be looking at your address maybe at a different corner of the globe and try to route packets to you. So, these addresses have to follow a global norm, okay, and that was used to be controlled by Internic, one central body. So, you have to have. Now, the number of addresses, now if you have to give it to somebody, gives the address to somebody, you have to give one entire network address for his particular network usually, alright. And now this creates a problem in the sense that when the demand for network these addresses becomes too high, you run out of addresses, okay. Actually, as a matter of fact, we have come to a stage today where we actually, for all practical purposes, we have run out of addresses. It is very scarce now. You only have a few class C addresses left. Now, if we had been much more careful, if we could have envisaged how the networks would grow, and if we had been much more careful earlier in assigning addresses and not waste big addresses like that, maybe we could have stretched this by a few more years. But anyway, this cannot be helped now. So, people are trying various types of workarounds for this particular problem, this shortage of IP addresses. That is one side, and the other side was that quite a number of years back people worked on a new protocol. If you must have noticed that this lecture is titled IP version 4, okay, possibly implying that there are other versions available, and actually there is IP version 6, which was finalized. It was finalized quite a few years back, and I will talk about IP version 6 later on in the next lecture. Anyway, so the IP version 4, we have this problem. So, various workarounds. Now, what kind of workarounds? One thing could be, if you take a big address chunk, let us say a class B address, okay, and give it to different organizations, some parts of it, okay. The one problem is that, first of all, you are breaking down these classes, class A, B, C, nice at the byte boundary you had it. So, the point was that do not have them at the byte boundary, alright. So, they are no longer belong to one particular class. So, they are called classless, and classless interdomain routing, that is the CIDR, that is a protocol which is there, where what you do is that you specify your starting address and then specify somehow that how many hosts you have in your particular network. So, this is an example. Suppose some say British universities like Cambridge, suppose the first address is this and the last address is this. That means how many nodes do they can have? You can have from 0 to 7, so that is 8 over here, and of course 256 on the last byte. So, 8 into 256, that is about 2048 hosts. So, it gives the starting address 194.24.0.0, then /21. This 21 is a code which really shows that there are 2048 hosts. Okay. Now there are various such numbers are possible. 22 means 1024 hosts, 20 means 4096 hosts. This way it goes down on one side, on the other side you can even have less than 1024 etc. hosts. So, there is a various numbers are there and there is a table, we did not bother about that right now. So, this really represents how many are there. So, there is a table that 21 means 2048, 22 means 1024, 20 means 4096 and so on. Okay. Similarly, 19 would mean 8000 hosts and so on. There is another workaround which people have done is actually many organizations are now doing it, which is the which is in common parlance it is called NATing. NAT is for NAT, that is Network Address Translation. So, what you do is that, as I said earlier, and now I am going to sort of contradict it a little, in the sense that, as I said earlier, that this address, your IP address has to be known globally, all right, because has to be a global standard, it has to be globally assigned. Okay. Now, we make an observation that this is true only when we are communicating, only when I am trying to communicate with somebody, or only when somebody else is trying to communicate with me, that is when it needs to be global. So, what you do is that you have an entirely private, so called private address, you use a private address, and if it is private, why not a class A address. Okay. So, whatever be the size of your organization, maybe you use a class A address inside. Okay. This class A address that you have just decided to use it without anybody's permission or without anybody's leave, which means that this address is not recognized globally, all right. So, you use that. So, do all your internal communication, I mean assuming that you are in a big organization. So, you do all your internal communication using this private address. The point is that only when you are going out to communicate with somebody, you will mask your private address, keep a table where there will be a table, the table will be a dynamic one. Okay. For the time being, there will be, suppose you want to communicate. So, dynamically there will be your local address, which is actually a private address, which is not really a legal globally legal private address. So, that you will put, and then you will have a pool of legal addresses, one of them whichever is free, that you will use, and then take out and then start communicating. So, to the outside world, it will be as if you are communicating with this particular legal address, which you have assumed for a temporary point of time while you are communicating. So, that is called network address translation. Suppose we have this company LAN, there is a company router, etc., and then a packet arrives, and suppose this has an address 10.0.0.1. Well, the first number is 10, which immediately tells you that this is a class A address, which is not really, this company does not have, let us say, a class A address, he is using it, and there is a convention that when you use private address, somehow you use 10. Okay. There is no great reason for that, but whenever somebody looks at an address which starts with 10, he knows that this is a private IP address. So, this is a private address that he is using. This is going through maybe, let us say, a NAT box or firewall. Okay. Now, this NATing could be done at a, can be done at a firewall, the NATing can be done in the router also. So, you could do this NATing in various, so all these boxes usually come with that capability. So, in this NAT box over here of this firewall, that maintains a table of this IP address is trying to communicate. So, it assign. So, this is assigned a pool of IP addresses. Out of that IP addresses, maybe this particular IP address 198.60.42.12, that is free at the moment. So, he will give that, he will take out this particular address, put in this particular address and send it to the outside world. So, the outside world will know the source to be this particular address. So, when the outside world replies back, it will come back here to this particular address. It will go through the same box, the box knows that this is really an address which is temporarily assigned to him. So, he will now take this out, put 10.0.0.1 and send the packet to the particular host in that particular network. So, the outside world will know that he is communicating with this fellow, whereas this is not really a fellow, this is just one of a pool of address which is shared by a large number of hosts, and the translation is done here. Okay. So, that is an example of how NATing is done. This is not entirely satisfactory, but this is used quite often. For example, in my organization IIT, we use NATing because we have got 10,000 more than 10,000 machines, and we do not have a class B address, can't be helped. So, we just have a bunch of class C addresses. So, we assign these class C addresses to all these boxes which do the NATing, and then that is how we communicate. One problem is that if the NAT box fails, all the connections are lost. That is one problem. It violates the OSI layer independency, because this is a workaround after all, because we do not have so many addresses that people demand. Some applications insert IP address as a part of the message, then of course that application will fail, because if the IP address is somehow hard coded inside the application message somewhere, that is not going to work. And NAT change the content of the IP datagram. This is incompatible with secure data communication. If you want to do the entire thing secure, including your IP addresses where you are communicating, this NAT will not work. Or wherever you are doing NATing, you cannot encrypt that part. Just one small point, that IP data is laid out in big endian order. That means byte transmission order is 0, 1, 2, 3. You know, big endian or little endian, that which way you go, 0, 1, 2, 3 or 3, 2, 1, 0. So, in networks, this is the network byte transmission order. Now, we want to look at the IP header. This IP header, we have version, header length, etc. And I will just tell you, just note that IP header is 20 bytes or more, it is minimum 20 bytes. So, this is 4 bytes each, so that is 32 bits each. The source IP address is given, so that is 4 bytes. The destination IP address is given, that is another 4 bytes, so that is 8 bytes gone. These 20 these 3 bytes, these 3 batches of 4 bytes each, that is these 12 bytes are for these various things which I will just describe, and later on there may be some options. Version number, well, this is 4 right now, so this is 4. If version 6 would be there, bit field specifying the IP version, currently 4. Header length specified in 32 bit words, range is from 5 to 15 words or 20 to 60 bytes. So, what is the length of the header? Why do I need the length of the header? If you look at the previous one previously, that there could be options. So, how do you know whether just after destination IP address the data starts, or the header goes some more and some options have been exercised? So, the header length has to be given. So, that is the header length. And then type of service, this was meant as that I mean what is some kind of quality of service was expected, but this did not work out very well. So, this is mostly ignored now. Message length in bytes, okay, what is the length of the message? Datagram identification field that must be unique. So, there is a datagram identification field, 16 bit packet identification. So, this is important. Why important? We will talk about it when we talk about fragmentation. Time to leave field, upper limit on the number of hops a message can go before being dropped. Although this is called time to leave, actually this is given by the number of hops. And why do you require that? Well, you require that because the point is, suppose the routers, you know, they work in a distributed fashion. We have seen this RIP and other protocols, they work in a distributed fashion, and there may be some problem somewhere. Now, because of that problem, you may get a routing loop. That means a packet will go on, I mean virtually that this loop is, since this loop is distributed, stored in a distributed fashion, nobody really detects that there is a loop, but actually one particular packet finds that this is just gone in a loop. Now, this packet, if it does not die out naturally, what will happen is that it will keep on circulating ad infinitum, and such packets will get accumulated and it will bring down the whole network. So, there is a mechanism, and there are other reasons for this of course, but there is a mechanism that if a packet has gone very much astray or if it is just circulating after some number of hops, a router will see that it has already crossed so many hops, this is its time to live. So, its time to live has come down to 0, so drop it. Otherwise, you just reduce the time to live by 1 and send it to the next hop. Now, there is a protocol which identifies TCP, UDP or ICMP. You remember that this is on the network layer. Now, above the network layer there is a transport layer. IP is the hourglass design which sort of concentrates in the IP from the various different types of network like Ethernet, token ring, etc. It comes to IP. From IP it goes to various different protocols like TCP, UDP and so on. Now, if it is going now how does it decide in the network layer, how does it decide where to go to, so whether to send it to the TCP in the transport layer or whether to send it to UDP in the transport layer. So, that must also be mentioned. So, this protocol identifier is there, whether it is TCP, UDP, ICMP, IGMP, etc. Header checksum of just the TCP IP header, that is this IP header. Source address which is 4 bytes 32 bits, destination address another IP address, this is again 32 bits, and options. Data starts at total length that is the header length, etc. And so, maximum IP datagram size is 64 kilobytes. Hosts are not required to receive packets greater than 576 bytes. That means but at least 576 bytes they have to accept. Ethernet MTU remember is only 1540 bytes. So, most implementation allow for about 8000 bytes for IP datagrams. The point is that when a particular packet has come to a network, the packet may be too large for that particular network to handle. So, so then something has to be done. One thing of course if you drop it, but if you drop it, I mean every time he wants to send the packet will get dropped. So, what is done is this packet is broken down into smaller parts called fragments, and these fragments are then sent through the network. Thank you. In the next lecture we are talking about IP version 6 and mobile IP. Thank you.